Okay, there we go. All right, so chapter 8 in your book deals with gases. The learning objectives here, we have gas as a pressure. So this one will introduce some pressure units that like the first chapter and second chapter, where we're introducing a lot of the things like the significant figures, a lot of the metric system. There are new units that you have to be able to convert from, okay? There are some simple gas laws called Charles, Boyles, and the combined law. Here, these are variables that we have to be able to functionally work around, okay? We should obviously have some general notion of what a gas is, okay? As you breathe in, we're breathing in gases, okay? We all understand that gases are a lot less dense, that they are compressible. Everybody's dealt with and or heard about compressed air or compressed CO2, all kinds of these various things, whether you're using an air compressor for tools for working around the house and stuff. By applying pressure, we can change the variables under which our molecules are in. So unlike our solids and our liquids, but they really couldn't change. You can't really change their volume that much, right? We can't really change their volume that much, and applying pressure to them doesn't really do much functionally to the chemistry, right? So we get a different situation with the gases. By being able to change those variables, we are able to change some of the reaction dynamics. Okay, so the ideal gas law is another one of these kind of laws here. This will introduce a different kind of dynamic in dealing with the amount of stuff that's in the chamber. And then we have partial pressure. So we want to be able to calculate these various things. And so this is dealing with when you have mixtures of gases. So because when we breathe in, we're breathing in nitrogen and oxygen and carbon dioxide. And so there's a mixture of stuff. And so that mixture, each one of those gases is contributing to the overall pressure of the system. So, but if we want to know about individual gases, then we want to pull a partial out, and we want to talk about the partial pressure of an individual gas. And then we have chemical reactions. So this will go back to our stoichiometry again. So I've kind of been talking about a flow chart or a process chart for dealing with the different stoichiometry. So this will essentially add another branch onto our stoichiometry, okay? And so in the previous chapter, we looked at aqueous solutions and chemical reactions. We also looked at solids and chemical reactions. But this chapter will introduce what happens if our product is a gas. Like if I have methane and carbon and oxygen, and I make CO2 and water, and the carbon dioxide is a gas that I'm producing, right? And I want to know what is the volume of gas being produced? You can't calculate that with molarity, right? Our molarity doesn't work, and we're not measuring how much, we're calculating the volume of gas. So it introduces some slightly different dynamics, but it fits in well with our process flow chart, and so it's not much different than what we've been doing, okay? Okay. So gas pressure, being able to convert various gas units, right? So we've talked about solids or aqueous solutions. So the difference here is not having a definite volume, okay? The expansion and contraction of gases and the change in volume of the entire container allow for us to change some of the other parameters of our reaction. What happens if I change the volume? How does that affect the other things? When we deal with pressure, okay, so pressure in most contexts is a force per area of unit, okay? So if you've taken any physics classes, you've talked about pressure at some point. And commonly in physics, like one of the examples that's given is like a nail. So you have a nail, and if you step on a nail, right? So your force is your body weight being applied to the area of the nail. So the tip of the nail is the area, and then you're applying your force to that. And then obviously that creates a rather large force, and then breaks the skin, and you have an injury. Whereas the guy that lays down on the bed of nails is distributing his body weight on the area is being spread out, and so his body weight is being dispersed across those things, and he doesn't get skin puncture. And so the force, in at least for various, like in physics, there's an actual unit of force, and then per unit of area, obviously area is measured in things like meters squared or centimeters squared and things like that. Okay. So in chemistry, we don't really have a force area or a force unit, right? So there's lots of applications of this. So one of the most common ways that we can talk about this, as I've already done, is talking about things like inhalation, where we're breathing in a gas, and so this changes the volume of our lungs. Okay, as our diaphragm moves up and down, you're changing the volume of your lungs. Okay, and so changing the volume causes pressure changes within the lungs, which allow for extraction of gas into the blood vessels, and also pushing gas out of the blood vessels back into the lungs. So it helps that gas diffusion by changing the pressure within the lungs as we inhale and exhale. Okay, so one of the other things here that we commonly see as far as air pressure or pressure on a daily basis is look at weather patterns. When they talk about things like a high pressure unit or a low pressure coming in, talking about atmospheric pressure. They're talking about the force of the air upon us. I'm not sure why this cut here in my PowerPoint. Okay. One of the other ways we commonly deal with things like pressure for us biologically, aside from just inhalation, is also things like our eardrums, right? So our ears maintains a general equilibrium with everything else around us, and the same thing with our ears. And so as you go through various pressure changes, right? So like when you're flying, you're in a pressurized tube, right? So they pressurize the cabin essentially, and so you're changing the pressure on your ear, or if you're thinking about, or if you're diving, right? So when you start going down in the water pressure is pushing down, and it's applying pressure on the membrane there, and that's why you got to blow and kind of equilibrate the pressure in your ear, so that way the pressure doesn't build up to where it becomes painful, right? So commonly how we start our discussion of things like pressure are dealing with the barometer. Okay, so this goes back to the discussion of atmospheric pressure. So we've talked about, or when you hear on the news, they talk about the barometer is falling or the barometer is rising. They're talking about a setup like this, where they have a tube of mercury, okay? And so they're looking at the height of the mercury in the container. And so this, again, harkens back to our physics stuff of equal and opposite forces. The atmospheric pressure pushing down is equal to the liquid pressure pushing up. All right, so these equal and opposite forces work, and so the height of the mercury in the tube is therefore a relation to the atmospheric pressure that's holding it up. Okay, so if the atmospheric pressure drops, then the volume in the tube begins to drop, right? Because if the atmospheric pressure is not pushing down as much, then as it lets up, then the volume in the tube, or the height in the tube, goes down. Or a lot of atmospheric pressure starts pushing down, it starts pushing the mercury up in the tube higher. And so we're able to equate atmospheric pressure to the height directly of the mercury in the container. Okay, so millimeters of mercury becomes an equivalent value to where we can compare things like atmospheric pressure. Okay, and so commonly you'll see things in millimeters of mercury, particularly if you get your blood pressure done at the doctor, or you're measuring blood pressure. It's usually this is it sphygmometer, I think is the instrument that they use, but it's measured in units of millimeters of mercury usually, right? Now the difference and the reason why we use mercury is because if we look at the difference of mercury versus water is based on this equation over here. The pressure is a function of the height of the fluid, the Greek symbol rho is density, and gravity, right? So the hydrostatic pressure is equal to these, and so the density of the liquid here is of water is so low that in order to reach atmospheric pressure, a barometer made of water is about 30 feet tall, right? So it's not functionally usable. So a barometer made out of mercury, it can be, a foot or so. So they're not overly very big. So it's, there's, they can be relatively small, I think, and they're relatively compact in like a lab or something, one that's like 2 feet tall or so. And you can get basically with the effect that you need. All right, so what we need to be able to do is to convert between different units. Okay, so here we have atmospheres, ATM. Now this is the common unit that we're going to be using for this course. Okay, almost everything is going to be in atmospheres, ATM. Okay, commonly there are other units called torr. Okay, or millimeters of mercury, right? These are basically the same unit. They have the same basic conversions. Okay, you have the Pascal. So the Pascal is really the physics term of which we kind of derive everything from, because the Pascal is a Newton meter squared. Okay, so remember the Newton was an actual unit of force. Okay, so if we have the actual unit of force per area, it's the purest real value for pressure that we can get. Okay, so the Pascal is the SI unit for pressure. Okay, and then you have things like the bar. Again, I don't know how often you come across these, but we should be able to convert between these various units, because again, if we talk about a chemist versus a physicist versus a doctor, everybody uses their own units, and so we want to have some general ability to maneuver between those different units. Okay, so everything here is in relation to 1 ATM. Okay, so since ATM is the most important unit for us, right, we want to convert to and from ATM. So 1 ATM is 760 torr, which is also 760 millimeters of mercury. Okay, in 1 ATM, all right, that didn't work out very well. Hang on, let me sorry. Let me just stop sharing. Let's go back to this. All right. Sorry, it's in 1 ATM, there's 101,325 pascals, right? So without the decimal place here, it's 101,000, right? 325. Or in kilopascals, it's 101.325 kilopascals. Okay. Again, the bar, I wouldn't really worry about saying it so much. There's in every book, as we change different books, there's always some rando unit that they throw in there. Like the last book we had was inches of mercury, and it's like I don't even know who even uses that. I'm sure there's some, asinine US, person that uses inches of mercury. But most everybody else uses the metric system. And so we're using millimeters of mercury for the most part. And so we want to be able to convert between those units. And so here's a practice problem where we are converting from PSI, so pounds. Oh, that was the other one that was missing off here. Okay. So pounds per square inch is a common unit that we come across, especially if you are looking at things like your tires, right? So if you're going to go put air in your tires and you look along the side of your rim, you're going to see that, it wants you to put 40 PSI in your tire. And so that's what you got to put the pressure gauge to on the machine, is to the PSI, the pounds per square inch. Okay. So I'll have to adjust my one slide here that includes that as well. So we don't have a relation for PSI to millimeters of mercury. So we have to kind of go through the intermediate of ATM, in which we can convert to everything else. Okay. So in 1 ATM, so this was missing off the previous slide, there's 14.7 PSI in 1 ATM. And then in 1 ATM, there's 760 millimeters of mercury. Okay, so this is the relation between these two and the relation between these two. Okay, and so starting out with the information we're given, the PSI, okay, there's 14.7 PSI in 1 ATM, and in 1 ATM, there's 760 millimeters of mercury. And so then that way it gives us our unit in millimeters of mercury. Okay. Setting up everything opposite cancels out those units, leaving me with just the unit that I was looking for. Okay, here's another one, another PSI here we have to kPa, okay, to kilopascal. Same basic setup here. We don't have a direct PSI to kPa value. So we want to be able to convert using the relationships. Okay, the 14.7 PSI to ATM is the one chip, and then the 101.325 kPa is our second relationship. Okay, so same basic setup here again. 45 PSI. There's 14.7 in 1 ATM and 1 ATM in 101.25 kPa. It's 314 kPa. Right. Now, usually on the test, I would say you need to have these memorized, okay? But you're working at home, so again, it's less arduous for the memorization that we're all going to pretend that we're do for these units. Okay, so if we were doing this in class, usually I give this, a summary slide here and say, you would have to know these because I wouldn't view these on the test. Okay, so on the test, there's not going to be a key on the test as this information likely. Okay, again, and especially because the other hard part here is, okay, so what I'll probably have to do is post an equation guide. Okay, so I will post an equation guide because this chapter is equation heavy. Okay, this chapter and the next chapter are equation heavy. So the last test, okay, this is not for this next test. This is for test 4. Okay, on test 4, there will be an equation sheet that goes with all this. Okay, which I will probably go ahead and put all this on there because I'll already assume that you would have it in front of you anyway. Okay, so normally if we were doing this in class, I would say you would have to have these memorized because I wouldn't give you these units. Okay. All right. So here we have a couple different ones here, converting torr to ATM and kilopascal to ATM. Okay. So again, okay, good question. So this stuff right now is not for the next test. This is for test 4. Okay. The next test is only chapter 7. Okay. Test 3 is only chapter 7. Okay, so this is already for the next test. This is for chapter 4, or the test 4. Okay, this is for the last test. All right, so like that, we're going to introduce some of this tonight. We'll come back to it next week. Again, we'll probably do the review mostly on Wednesday for the test. I'm still, so this kind of goes back to, again, we're still going to do it the same way we did before. I'm still going to have class next Monday. I'm not, we're not sitting down and everybody staring at each other over the internet to see when you take your test. So you have 2 days to take the test. So we're just going to keep having lectures. So we're a little bit ahead here, right? But we'll do some review on Wednesday for the next test. But it's only on chapter 7 for the next test. Okay. So here it's torr to ATM. It's only the one conversion. There's 760 torr and 1 ATM. Right, so you're dividing these numbers, and so you get 0.85 ATM. Okay, same thing with the kilopascal. We are converting from, we have a direct conversion of kilopascal to ATM, and so it's just dividing that unit to get the ATM we want. Okay. All right, so let's take a look at simple gas laws, and then we'll take a break here. Okay. So usually I get to get through the ideal gas law in the first lecture of this, because the mixtures and stuff, it takes time. We could be here for a while just talking about all the different mixture stuff. So so usually I wrap up around that, covering the basic gas laws and the ideal gas law, and then we'll tackle the other stuff in our next lecture. All right. Here we want to be able to use the various conditions that we have in order to find other conditions that we're given. All right. So this is called Boyles Law. So this is a chemical law. All right, so this is probably one of our first. It's probably not the first one that we've really talked about, because there's been other laws that we've talked about, but probably not as directly as this. So Boyles Law deals with the relationship between volume and pressure. Okay, so the important thing here to know is what's in bold. Okay, is that if we're holding temperature constant, okay, pressure and volume are inversely proportional to one another. Okay, if I press down on the balloon, okay, I'm putting pressure on the balloon. Right, I'm increasing my pressure. My pressure is going up, and my volume of my balloon is going down. Okay, so as I'm pressing on the balloon, the volume is getting smaller. So they are inversely related to one another. Okay, so here we can see the pressure here is in the weight being applied to the cylinder. Okay, 1 kilogram versus 2 kilogram. Here I've doubled the pressure, and so it changes the volume. Here I double the pressure again, it changes the volume again. So as pressure increases, the volume decreases. Okay, and so this gets you to this equation. All right, so like I said, there is an equation sheet. You don't have to memorize the equations, you just have to know how to use them. Okay, so P1 V1 equals P2 V2. So you'll recognize this one. It looks a lot like the acid-base equation we did. It looks a lot like the dilution equation we did. Okay, and the problems are generally just as easy to solve as the dilution and the acid-base one. The only time that you get into kind of weird problems with this is like if you're working out of like an older book like Silverberg or something. They would give you random units for all 4 of these, and then you had to spend time putting everything into similar units in order to even put them together. Because if I give you ATM and kilopascals, you can't divide ATM and kilopascal. Okay, that should be obvious, right? So you have to put both of them into the same unit. So the pressure has to be the same unit on both sides. The volumes have to be the same units on both sides. Okay, they don't have to be liters, but they have to be the same. Okay, they don't both have to be ATM, but they do have to be the same. Okay, so they can both be in torr, they can both be in kilopascal, they just need to be the same on both sides. Okay, and so in talking about respiration, this is essentially the laws with our respiration. Okay, our body temperature doesn't change, right? So our body maintains homeostasis, so it functionally keeps a relatively same temperature, not enough that affects any of the gases anyway. So even if you're running a fever, that doesn't affect like really the gas, you know, too much. Okay, so as your diaphragm contracts, okay, the volume is going up. Okay, this causes a pressure drop, which helps the gas diffuse into the bloodstream, versus when the diaphragm contracts, the volume is going down, increasing the pressure, which forces things out of the blood and into the lungs that we can exhale. Okay, so this relationship is how our lungs operate, is called Boyles Law. Okay. So you'll notice most of these problems are pretty straightforward. They look a lot like this in most contexts, right? You have 3 out of 4 terms, okay? A 3-liter sample of hydrogen has a pressure of 0.75 atm. What is the volume if the pressure is increased to 1.5 atm? Okay, so we're essentially given 3 out of the 4 terms. Okay, so you can rearrange it to start with. Here we have a pressure, okay, the 0.75. We have its volume at 3 liters. So what is the volume when we change it to 1.5 atm? All right, there's supposed to be a dividing line in here. Not quite sure where that. That's weird. All right, let's go back and check that. All right, so obviously it's supposed to divide, right? There's supposed to be a division of the volume. All right, this one here looks a little bit better when we look at it. Right, same kind of setup here. This one sets up a little easier. Here you go. So this one looks better in its setup, right? So we're told 1.545 liter sample of argon has a pressure of 0.95 atm. So the 0.9 and the 1.5 are one side. Okay, so that's one side. And then it's increased in pressure to 787 torr. So this is where, this is like I said, this is kind of like how they throw the wrench in here, is by making these units different. So you can't just put those units together. You got to do a first conversion up front to convert the 787 into ATM. Okay, so that's where the 1.036 comes from in the bottom, right? Is the conversion of the 787, right? So you've got to convert those units before you can use them. Okay. All right. So our next one is dealing with Charles' law. Okay. So Charles, J.C. Charles dealt with looking at gases, but here the relation was keeping pressure constant and changing temperature. Okay. So one of the things that that comes out of this is looking at an experiment here. Pressure is held constant and the temperature is reduced. So we see a linear relationship between volume and temperature. So as the temperature drops, the volume goes down. Okay, they work together, right? So as they are linearly related to one another. Okay, and so what also came out of this experiment was also at some point there's an extrapolation back, like what would happen if you brought this, how far back would you go? So you'll notice here that it's zero volume, okay? Well, obviously we can't have zero volume, right? Everything occupies a space, so everything has some sort of volume. So it's a theoretical value of what happens at that point. Now, this also coincides with what is negative, or is 0 degrees Kelvin. Okay, so 0 degrees Kelvin, we talked about Kelvin scale before as an absolute scale. So absolute 0 is the bottom end of the Kelvin scale. And so what we find here is that, this also relates to absolute 0 and what happens at absolute 0. So we see a 0 volume, which can't reach, but also at that point, we also see things like the stopping of the motion of electrons. Again, electrons don't stop moving, so we would functionally stop all movement of mass at 0 Kelvin, at absolute 0, right? So the takeaway here is change in temperature directly relates to the change in volume. Okay, if you increase the temperature, you increase the volume. Okay, so this goes into a variety of experiments that we can. I don't know if they have videos in here or not. So we have Kelvin. Okay, so we have V1 over T1 equals V2 over T2. Okay, so this is the Boyles Law equation. Okay, so in the Boyles Law, when it didn't matter what units you were using, you could do everything in Pascal, you could do everything in ATM. It didn't matter which volume units. In this one, there is a limitation. The units for temperature must be in Kelvin. Okay, because you can't use Celsius, because what happens when it's 0 degrees Celsius? You can't divide by 0. Right? So it doesn't work mathematically. So we can't use a scale where 0 is a possibility. Okay, there is no 0, we can't reach 0 degrees Kelvin, so therefore the absolute scale works out best for us here. So these temperatures must be in Kelvin in order to proceed with this. Okay. And so, like I said, so this, looking at a variety of experiments, and they all extrapolate back to this point. And when you see data like this convergence of data, it means there's something important. There has to be some meaning if you do a bunch of experiments and all of the data leads back to one point, right? That has to mean something. And so this convergence of data leads us back to absolute 0. All right. Let's see if my video work. Okay, so can you guys see the video? The video playing okay for you guys? Okay. Okay. So essentially what you've got is a chemistry or physics class being outside. They have a 55-gallon drum. They are heating it with a propane heater, okay? And so they've got water in there, and so heating it up, so the temperatures, they're raising the temperature up, right? And so what happens when they bring the temperature back down? Okay, so here they're capping it, right?
Twist.
Okay.
Squeeze. Insurance.
Patience, my child.
Oh no, my God, the stopper is
It's a lot of volume, so that's why they're.
No, throw the some water on it. Oh no, just grab the ice unit with your hands. That is so wimpy.
It's what you need it for. Okay, so we get the crushing of a 55-gallon drum, essentially by application of law. Okay. All right. So then we have the same kind of problems we'll see here with the use of Charles law. You'll have 3 out of the 4 terms. We have a gas that's at a volume of 2.5 liters at 0 degrees Celsius. What is the volume goes up to 2.8 liters. Okay, so again, our only consideration here is turning our units to Kelvin. Okay, so remember how to convert from Celsius to Kelvin. Important to remember here, because again, if we don't remember how to do that, we're just adding and subtracting 273 to convert things to and from Kelvin. Okay, so putting things in with the Kelvin, the volume's in there, it's a line divide, and they get the Kelvin unit of the new temperature. Okay. Same kind of problem. Again, it's multiply and divide. This stuff is relatively straightforward. All right, so before we get into the next, all right, so the last one here is the combined gas law. There's really nothing different here. This is just combining Charles and Boyles law together. So you have the relationship, the P1V1 over T1 equals P2V2 over T2. And so this is just like if you have all these different variables, inevitably you get a problem where they're changing all 3 of the variables, or changing 2 variables, and they want to know what is the outcome if of the third term if you change these other variables. Okay, so it doesn't functionally change anything. Same kind of setup here, that the temperatures have to be in Kelvin. Okay, same thing applies for the Charles and Boyles law respectively. Okay, so the pressure and volumes can be whatever whatever they are, as long as they're the same on both sides. All right, we'll come back to this practice problem. And so let's go ahead and take a break here. All right, so I'm gonna take 5 minutes because I need a drink. So let's pause. Okay, so in the ideal gas law, here now we have the addition of moles, so the amount of stuff that's there. And so we can calculate things like molecular weight and density as well. So we already had the pressure and volume and temperature as units. All right, so here is the ideal gas law. Okay, PV equals nRT. So what you'll have here is you have pressure. Okay, P is pressure, V is the volume, N is the number of moles, R is a gas constant, and T is the temperature. Okay, so pressure here, so the one driving factor is the ideal gas constant, okay, which is this, 0.08206 liter ATM per mole Kelvin. Okay, so it's kind of like the Rosetta Stone unit, right? So it allows us to convert from one thing to another thing and get the right units, okay? Because obviously if we put pressure ATM times liters, we're not gonna get moles, right? So the gas constant allows us to convert those units to one another, right? So pressure, so that means that these things all have to be in these units, okay? So pressure has to be in ATM. Volume has to be in liters. Moles, obviously, and Kelvin has to be the temperature. Okay, so everything here has to be these particular units. All right, so the ideal gas law, let's see what the next slide is. So the ideal gas law is an approximation of how gases behave. Okay, when we have gases, there are all kinds of other factors that play a role in here, not just the pressure, the temperature, the volume, the amount of stuff, right? The molecules of gas themselves play a role in the reactions, right? If you have very big gas molecules, okay, very large atoms of like, krypton or xenon, you have these big atoms and they have a lot of electrons, as we've seen them before. And so when they run into one another, okay, probably not the noble gases, but something like bromine and iodine, or these very heavy gases that are going to interact with one another, as they slam into one another, those electrons, they're either going to cause some sort of reaction where they're going to react, like you got nitrogens and oxygens, and will they get stuck together? Well, if we apply enough pressure, right? If I take air and I apply enough pressure, the nitrogen will fuse with the oxygen and make a new molecule, right? So there's attraction and repulsion forces that are at play with these molecules as well. How big they are, how much they're bumping into other stuff plays a role in how they interact with other stuff. But the ideal gas law says that we're not going to look at those things. We're going to ignore external factors and just focus on the gases themselves. Usually my analogy, because everybody's sitting in a classroom together, is that if everyone was in the classroom together and everybody got up and started running around, the ideal gas law says that you're not going to run into anything, and there's no attraction and repulsion forces between everybody. Okay, so obviously you have, boys and girls, and so you're going to get, attraction between opposite sexes, repulsion of same sexes, maybe, but in any case, gases are like that. So or molecules are like, you're going to get attraction and repulsion, and you're going to get things bumping into one another. So we're assuming that none of those things are real. But as we get to real gases, so when you start up in high enough pressure, okay, when you start taking the pressure up, the ideal behavior begins to deviate, okay, which is where, again, this is 200 ATM. So, I mean, normal atmospheric pressure is 1 ATM. Okay, so we're starting to put some non-ideal conditions on our gases here. So it's realistic that at some point your model is going to break down, right? So think of it like Newtonian physics, right? Newtonian physics works fine for regular objects floating around the solar system. But when you're starting to do something that's maybe not quite as normal as everything else, like Mercury's orbit, or as we start getting down into really small objects, that same kind of physics doesn't work as well, right? We need a more fine-tuned equation in order to reflect the actual behavior of things. Okay, so your big fat paintbrush works fine. If you're painting most of the house, it works fine for everything. But if you're trying to really paint something like a little figurine or something, that big 4-inch paintbrush isn't going to do you any good if you're trying to paint like a little figurine. You got some Star Wars collectible you're gonna hand model, that hand paint. That 4-inch brush ain't going to do you any good, right? So you need something slightly different that's going to apply a little more fine tune, right? And so what you get is this, okay? Now, we're not going to deal with this at all, okay? That's why there's no little star on our slides over here, okay? So this is the van der Waals equation, which is the more realistic equation that takes into account things like size and attraction and repulsion forces. So you can already tell that with that square in there, that's going to make a mess out of trying to do these to do this equation. So the ideal gas law is much more preferable for most of our circumstances that we have to deal with. Okay. All right. So here we have an equation. How many moles of gas are in a basketball? Total pressure 24 psi. Volume is 3.24 liters at 25 degrees C. Okay. So one of the giveaways here is if it's asking for moles, more than likely, you're gonna have to use the ideal gas law. Okay. Most of the other equations don't have moles in them. So if it's looking for moles or it gives you moles, a good chance is you're gonna end up using the ideal gas law in order to do the equation. Okay. Again, the same setup here is kind of a problem, is that everything has to be in these particular units of the gas law, right? So we have to convert some things, okay? So our PSI, again, back to those first units that didn't have PSI on them, but they should. So the PSI to ATM, okay? And my temperature, 25 degrees C to Kelvin, 298, okay? And then we can plug everything in to our equation. And so these tend to be very plug and chug. So most of these problems look very much like this. There's not a whole lot of variation, at least not in very straightforward kinds of problems like these, where we have 3 out of the 4 terms, we have the constant R, that's a constant that's given to you, okay? You'll have that on your equation sheet. And so it's really just plugging these in and smashing out the results out of our calculator, okay? And so we get 0.219 moles with a little multiply and divide. Okay, and those units go away, leaving us with, okay, there's the mole on the bottom, but it's dividing by a fraction, so that brings the mole up to the top as the main unit that's left over. Okay, like I said, when we do a practice problem on this, I'll look at the unit analysis and show you where the units come from. All right, so because of this, because we have so many variables that we have to work from, and if I'm a chemist and I'm in the lab and I'm doing some sort of experiment and I get some sort of fantastic result, I need to be able to compare that, okay? So we need to have some sort of conditions under which we can compare and contrast results. And so this is how we get our standard conditions, okay? Where if you've ever seen the CRC, okay, it's I forget what the acronym stands for, but it's basically like a fat book of just everything you want to know about any molecule like ever thought up, and it talks about things like, what is its boiling point, what's its melting point, what's its pressure and vapor pressure and melting temperature and all these other physical properties, and someone keeps track of all these things. And so at some point we have to have standard conditions, because if we're doing things like combustion, right? So some molecules are easy to combust, some are not. So, but how do we compare apples and apples so that we have some general idea of, comparable, heats of formation, of how much heat it's required to make molecules? So the standard condition, or standard temperature and pressure. So standard is 1 atm, so our normal atmospheric pressure, and our standard temperature is 0 degrees Celsius or 273 Kelvin, okay? So the reason why this is important here is you need to have this memorized, okay? Because the problems will just reference STP. So if you don't remember what STP stands for, then it may look like you're not given enough information. Or if you don't know exactly what it is and you put in the wrong number, then you're gonna get something miscalculated, okay? So here we have a gas occupies 10 liters at 44 psi and 27 degrees C. what volume will it occupy as standard conditions? Okay, so it's given us three terms. Okay, we've got volume, pressure, and temperature, and whatever the standard conditions are. So we don't know that it also gives me my pressure and temperature. Then it may look like we don't have enough information. Okay. Okay, hang on. So this slide also introduces another issue of this chapter, is that there are more than one way to solve some of these problems. Okay, now this particular slide, so we'll redo this. So what I would do is I would redo this, okay, this problem, not how the slide does it, okay? I would cycle back to the combined gas law and redo this problem with that, okay? You have V1, P1, and T1. Then you also have standard pressure, 1 atm, and standard temperature, 273. So you have, P2 and T2, and you're only missing V2. So you can plug it right into that and solve for the missing condition. In this case, what they do is they plug it all into the ideal gas law, okay, because the gas here, the 10 liters of gas, to start with, you're assuming that it's in a sealed container. It's not going anywhere, right? So all the moles of gas that are in there are the same amount of gas that's in there as you move it to STP, okay? So they look at how many moles of stuff is in there to start with, and then they use that to calculate the second volume under these new conditions. Okay, so this is one way of doing it. The other way would be to do the combined gas law. Okay, so here's the results of their first one. Okay, so they convert the PSI to ATM and the temperature to Kelvin. All right, so here, this one is just finding out how many moles are in the system. Again, the moles are not changing from condition 1 to condition 2. Okay, so at STP, they still have this many moles. Right, it's like a sealed container. Think of it like a balloon, right? So if the balloon is 10 liters big at 27 degrees C, how big is it going to be if you freeze it, right? If you bring it down to freezing and normal atmospheric pressure, right? So this is 3 atm, okay? So if we bring the pressure down, what's going to happen to our balloon, right? All right, so step 2 here is to take this mole and plug that in over here. So you have R as a constant. Now we have, here's STP, the standard temperature and pressure, giving me my new volume at this condition. Okay, so there's two ways to solve this problem. Okay, both of them will get you the answer. It's just a matter of recognizing what is the best way to go about this. Okay, and both these are just as reasonable. Okay. Now, a variation on the ideal gas law deals with density. Okay, because we can rearrange. I don't know if there's a rearrangement here. It doesn't look like it. All right, so until I have my pen and paper out, you'll have to take my word for it that this is a rearrangement of the ideal gas law. Okay, we have moles and we have volume, right? So the only difference here is grams. Well, how do we convert moles to grams? Well, we use the molecular weight. So by multiplying by the molecular weight, by multiplying both sides of the ideal gas law by the molecular weight, we get mass into our equation, right? But we do it to both sides, and so it gets rid of so your grams per mole is over here, you still have your moles over here, and so it ends up with mass in grams per liter for your density at the end, okay? And so again, this is another equation that would show up on your equation sheet. So key kind of giveaways here, obviously if it's asking for density, like in this problem, calculate the pressure of oxygen, which has a density of 1.44. If it gives you density, there's only one equation that has density in it. So it's probably a good choice that this is probably the one you're going to end up using. Or if it wants you to solve for molecular weight, again, you can solve from the molecular weight from the ideal gas law. You don't need to use this equation. We can get there from the ideal gas law. Okay, it's just this is a little simpler because it's a direct equation that puts everything nice and neat for us. Okay, so your molecular weight, you got our gas constant, temperature is 293, so it's converting our 22 to 295 Kelvin. Okay, and plugging everything in here. Okay, we're solving for pressure. Okay, we're solving for pressure. So it's just a little rearrangement of our top equation, right? So if I'm solving for pressure, I'm going to bring everything out from the pressure, right? So I'm going to divide the molecular weight, multiply the R, multiply the T, okay? So you get the R and the T and the molecular weight. We have all of these terms where we have everything. The only thing we're missing is the pressure, which doesn't give you the answer. So we can work on that one later, okay? All right, so that is pretty much everything I wanted to get through, at least for this first lecture here.